Hello friends, welcome to the video tutorial on basic introduction to VREP. In this tutorial, we are going to learn the following concepts. What is VREP, user manual and its main features, user interface, pages, views and scenes, camera navigation, position, orientation manipulation, simulation settings, physics engines, simulation scripts, and other necessary tools required for the theme. What is VREP? VREP, Virtual Robotic Experimentation Platform, is a general purpose robot simulator developed by Copelia Robotics. Let's launch VREP. Open the terminal, go to the VREP folder. In my case, it is in downloads, and launch VREP by typing /vrep.sh. Here it is. Now, for the user manual, go to Help menu and select Help Topics. So this is the entire VREP user manual explaining each and every concept related to VREP, its features, user interface, scenes and models, entities, calculation modules, how to write code in VREP, simulation. So this manual is a good guidance to learn VREP, which already comes as you install VREP. So let's look at the main features. So we can see here are some main features. First one is 6 programming approaches. VREP is based on a distributed control architecture, that is, each object or model can be individually controlled via an embedded script, a plugin, a ROS node, a remote API client or a custom solution. This is because VREP is very versatile and ideal for multi-robot applications. The second feature is powerful APIs along with 7 languages. In VREP, there are more than 500 functions, or you can say powerful APIs, to control the simulation, to write your script in VREP and simulate any robot. The third is remote API. In VREP, by default you can write script in Lua language, but if you want to write script in some another languages, remote API helps you to do so. Using remote API, controllers can be written in C, C++, Python, Java, Lua, MATLAB, Octave or Urbi. There are other features also like collision detection, minimum distance calculation, path planning, motion planning, etc. Let's see about user interface. Scenes. When you launch the VREP application, it is initialized with one default scene. As we can see over here, blue background along with this grey floor. The user is free to open several scenes in parallel. Inside this scene, you can pick and place any model and run the simulation. You can build any model using the primitive shapes or compound shapes inside the scene. Next, scene hierarchy and model browser. To better understand scene hierarchy, let's open one scene. Go to Files, Open Scene and select Linear Tracer threaded.ttd file. Open it. So this is the scene of line tracer robot. To the left of the scene, you can see the panel of scene hierarchy. It displays the content of a scene, that is, all scene objects composing a scene. So as you expand the line tracer object, you can see various objects that are present inside this scene. This line tracer is a scene object. Such scene objects are built in a hierarchy-like structure. Hence, the scene hierarchy displays a tree of this hierarchy. That is, a dynamic body is a parent of body, force sensor, body transparent, dynamic left joint, etc. Each individual element inside the scene hierarchy can be expanded or collapsed by clicking on the plus and minus button. So as I double click on the dynamic body, we can see the dialog box for the properties of that object, which we will see in the upcoming videos. So as I double click on the dynamic body, I can edit the name of that particular object. Let's say I am giving the name as dynamic robot body. So we can see that the name of that particular object has been changed to dynamic robot body. Next is model browser. To the left of scene hierarchy is the panel of model browser. It displays in its upper part a VREP model folder structure. That is, you can go to files and click on load model. So you can see that the contents of this model folder are displayed in the upper part of the model browser, and in its lower part, the thumbnails of the models that are contained in the selected folder are displayed. So these are the models that are currently present in the non-mobile folder. If you select mobile folder, so this particular models are there. If you want to load any particular model inside the scene, you just have to drag and drop that particular model into the scene. So for now, we close this scene. Next is status bar. It displays information related to performed operations, commands, and also displays error messages from the Lua interpreter. So as you can see, the previous command that I executed was deleting the model. So we can see that it is displayed in this status bar as deleting selection. So any command that I execute, if I just press undo, it will show in the status bar, executing undo and done. If I do redo, it will show executing redo. As you will learn Lua scripting in further videos, you can display the value of the variables used inside your script and also output strings to this status bar using sim add status bar message function. Next is menu bar. This is the menu bar over here. The menu bar allows accessing almost all the functionalities of this simulator. Most of the functions in this menu bar can also alternatively be accessed through a pop-up menu or through a double click on an icon in the scene hierarchy or from toolbar buttons. So as we had earlier opened the scene object properties by double clicking on dynamic body, similarly you can open it from tools menu. Next is pop-up menus. Pop-up menus are the menus that appear on the right click of your mouse. So as you can see, this pop-up menu allows us to access some functions over here that are also there in the menu bar. Now each surface within the application window, say scene hierarchy view, this scene, etc., triggers a different pop-up menu. In other words, pop-up menus are context sensitive. So if you right click on this scene, these are the set of functions that are available. If you right click in the scene hierarchy, the available functions will be different. Next is page selector button. So let's open a new scene and select page selector button. So each scene contains up to 8 pages and each of them contains an unlimited number of views. So in other words, a page is a container for views. So this is the view of the scene from one direction. This is from the other direction. This is a top view. This is a combined view from top as well as from one particular angle. Now next is scene selector button. So as we have opened two scenes over here, let's open one more scene, say epoch demo. So we are having 3 scenes in total. Click on the scene selector button. You can see 3 scenes together. So using this scene selector button, you can switch between the scenes. Next are camera navigation buttons. So the buttons on this top left are camera navigation buttons. So the first one is camera pan button. Using this camera pan, you can move the scene up and down, left and right to view all the components in the scene. Using the wheel of your mouse, you can zoom in and out into the scene. Next is camera rotate. You can rotate the view of camera in clockwise or anti-clockwise direction. Next is camera shift. Using this button, you can move farther and nearer into the scene. The last one is fit to view. This fit to view button fits all the objects that are there into the scene. So if I zoom into this scene and then click on fit to view, it again fits all the objects inside the scene. Next is position orientation manipulation. The first one is object translation button. For now, we close this epoch demo and line tracer scenes. To understand this object translation button, I am opening a scene that I have created to explain this button. So this is the scene. You will learn how to create such primitive shapes and joints and also their parent-child relationship in the upcoming videos. For now, the intention of this scene is to just help you understand this object translation and rotation buttons. In this dialog box, there are 4 tabs. The first one is mouse translation. Let's select any object. I am selecting a cuboid. So there are 3 options relative to world, parent frame and own frame. Let's select world. With respect to the world frame, that is with respect to the X, Y and Z axis as shown in this bottom corner. So if I just click on the cuboid, I can see the X and Y plane that are matching with the world frame. So this means that the cuboid can be translated in this XY plane only. If I wish to translate the object along other axis, I can just in which axis I want to translate it. So let's say I am selecting as YZ. So this is the YZ plane. So I can just move the object inside this YZ plane. So let us undo the previous command. The second option is parent frame. Inside this scene hierarchy, we can see that cuboid is the child of cylinder, and we can see the orientation of the X and Y axis of the cylinder are not same as that of the world frame. The red represents the X axis and the green as Y axis. So if we translate the cuboid with respect to parent frame in the XY plane, so as we select the cuboid, we can see the X and Y axis are oriented with respect to the cylinder's X and Y axis and are not oriented with respect to this world frame. So you can see the change when you are selecting the option related to world and related to parent frame. And when you select own frame, you can see over here that the x-axis of this cuboid in some another direction, also the y-axis is in some other direction and are not matching with the x and y axis of the world frame. So on selecting own frame, we can see the x and y axis are oriented with respect to the frame of the cuboid and not with respect to the world frame. So this is the difference between world parent and own frame. Next step is position. So let's say I am moving this cuboid to some another position in this XY plane, and now I want to bring back the origin of cuboid to the origin of this revolute joint. So go to the position tab and we select relative to world, control select the revolute joint and click on apply to selection. So we can see that the cuboid origin is coinciding with the origin of the revolute joint. Let's undo it. You can also apply this operation using one axis at a time. Apply X to selection, Y and Z. If you select parent frame, and then control select the revolute joint and click on apply to selection, you can see that cuboid is not positioned at the revolute joint's origin. This is because the parent frame, that is the frame of cylinder, is not as oriented with respect to the world frame. So this position of the cuboid is with respect to the X and Y axis of the cylinder. Next is translation tab. This is a manual option of translating a particular object along X, Y and Z axis by giving some values. So let's say I am translating the cuboid by 0.1 meter in X direction. So as I select X translate selection, the cuboid position gets shifted in X direction by 0.1. If I give 0.1 in Y, so you can see the coordinate of cuboid along the y-axis changes as you select Y translate selection. Next is position scaling. This is just to scale the position of this cuboid with respect to the world and parent frame. So let's undo all the changes that we had made earlier. Now the next is object rotation button. This dialog box is also similar to the translation button. There are three tabs: mouse, orientation and rotation. So let's select the cuboid. So similarly there are three options over here: world, parent and own frame. You can select the axis about which the object has to be rotated. So let's say I am selecting Z and then select this cuboid. The cuboid rotates along this Z axis. If I select the X axis, the cuboid will rotate along the X axis of the world frame. If we select parent frame and I select the Y axis, we can see that the y-axis of the cylinder is oriented in this direction, so the cuboid is rotated with respect to that y-axis. You can also select own frame to rotate the cuboid with respect to its own frame. Next is orientation. This is similar to the position in the translation dialog box. Now you can see the alpha, beta, gamma angles of the cuboid as 0, 0, 45 and of the cuboid as 0, 0, minus 65. Now if I want to orient this cuboid with respect to the cylinder, select the cuboid and Ctrl select the cylinder and click on apply to selection. So we can see that the alpha, beta and gamma angles of the cuboid have now been changed to that of the cylinder. Next is the rotation tab. This is same as the translation tab in the position manipulation dialog box. So if I rotate this cuboid by 90 degrees with respect to the own frame and click on X rotate selection, so we can see that the axis positions has been changed. If I give the value as 45 degrees, so you can see the change over here. The cuboid has been rotated by 45 degrees with respect to its own frame. Next is simulation settings. There are 3 buttons of simulation: start, pause and stop. There is one more for simulation settings. Now let's open the scene that we had opened earlier, that is line tracer threaded. So these are the 3 simulation buttons: start, pause and stop. As you click on start simulation, the robot starts tracing the line placed inside this scene. On clicking on pause, the simulation gets paused, and on clicking on stop simulation, the simulation stops. This is the button of simulation settings. This is its dialog box. These are the options. First one is pause when simulation time is higher than a particular number of seconds, which means that, let's say if we give the value of 10, the simulation will stop when the time exceeds 10 seconds. The other is pause on script error, which means that the simulation will stop whenever an error is encountered in the script. The rest options are self-explanatory. Next are physics engines. There are 4 types of physics engines that are available in VREP: bullet physics, open dynamics engine, vortex dynamics and Newton dynamics. Whenever you open VREP, the dynamics engine is selected to bullet 2.78 as default, and this is highly preferable. But if you want to read the documentation related to other engines, you can go to user manuals, and under the calculation modules, you can click on dynamics and read the documentation related to all the 4 engines. The pros and cons of each engine are also depicted in this manual. Next is simulation scripts. In VREP, there are 4 types of simulation scripts: main script, contact callback script, and these 2 are called as associated scripts, child scripts and joint control callback scripts. For our theme, we have to just focus on main script and child scripts. The rest 2 are not important over here. So this is the icon of the main script. So whenever you open a new scene, it is by default loaded with this main script. it is highly recommended that you do not edit or customize this main script. Child scripts are of two types, non-threaded and threaded. So these are the symbols of the scripts that are associated with the particular object. By double clicking on this symbol, you can open the script that is written. So you can see that this is a threaded child script and the robot traverses this line according to the script written over here. Similarly, there are non-threaded child scripts that are associated with the gate. Now you can look into the difference between the threaded and non-threaded child scripts under writing code in VREP, embedded scripts, simulation scripts, main and child scripts, and then child scripts. So non-threaded child scripts are pass-through scripts. This means that every time they are called, they should perform some task and then return control. If control is not written, then this whole simulation halts. Such scripts operate as a functions and are called by main script twice per simulation step. Also, it is instructed over here that non-threaded child scripts should always be chosen over threaded child scripts whenever possible. So we will look into the details of the non-threaded child scripts in the upcoming videos. Threaded child scripts. These are the scripts that are launched in a thread. The launch of threaded child scripts is handled by the default main script code. Such scripts have several weaknesses compared to non-threaded child scripts if they are not programmed appropriately. They are more resource sensitive, they can waste some processing time, and they can be a little bit less responsive to a simulation stop command. These are the other necessary tools that we will see over here. First is user settings. This is the button of user settings, and this is the dialog box of user settings. So there are options such as translation step size, rotation step size, so these are similar to as we had done in this particular scene. So if we are rotating this particular object, so for one movement of mouse, the object is rotated by 5 degrees. So if I change the rotation step size to 1 degree, so we can see that the change has been reduced to 1 degree step. Similarly for translation, if I translate the object for one movement of mouse, the translation is of 0.025 meters. If I change it to 0.05, the translation step size also reduces, and we can translate the object in the step size of 0.005. The other options in this dialog box are not necessary right now. Layers. This is the layers button over here. The top 8 checkboxes are the various camera visibility layers. If suppose I am opening the object properties for this cuboid by double clicking on the icon, and under the common tab, and I am keeping this cuboid under the fourth visibility layer. And if I uncheck the fourth box in the layers, the cuboid is not visible. This means that various objects inside this scene can be placed in different visibility layers, and we can hide and unhide the objects belonging to one particular layer by just checking and unchecking that particular layer in the layers dialog box. Next is video recorder. So this is the button of video recorder. Let's say I want to record the video of this simulation. So I can check this box saying that launch at next simulation start. So this video recorder will record the video when I will start the simulation next time. The rest options are self-explanatory. Also, you can choose the location where you want to save that particular video. The other tools are scene object properties, calculation module properties, and collections. We will look at them in the upcoming videos. Thank you.